Okay, and what I'm going to do is I'm going to play with you guys just a little bit. We're going to mess with this one. We're going to test this. We're just going to work with proportions for now. All right, these two guys. All right, so we'll transfer them over here. We'll deal with them one at a time. So the first thing that we're going to do is we're going to deal with the claim that 3/4 of adults use the internet. All right, and we've got our null hypothesis, which always contains the equality, and we're doing a test around a proportion, so 0.75 or 3/4. And our alternative hypothesis, since I don't have any other information, it's either equal or it's not, and we're going to go not equal to 0.75. Now, we're going to get into this in class, what exactly alpha is, all right? But I think you're going to start being able to figure out, based on what we've messed around with alpha before, what it is. But I'm going to test this at alpha equals 0.05. And I'm going to make up some information, okay? First and foremost, I'm going to say that we took 3,011 people, all right? And we asked them, do you use the internet? Okay? And let's say, so I got n equals 3,011. Let's say that 73% of them, so 73% said yes. All right? Now what I want to know is this claim validated with this information? Now, bear with me for just a sec. We're gonna kind of explore this problem and take our time with it. And I'm gonna show you a few ways to play with it. All right. Now, first things first. Let's identify what we know. I know that p hat, because remember we took a sample of 3,011 and approximately 37%. This could be off by some decimals. Said that yes, they use the internet. Now, you may automatically say, well, Ripley, okay, this is different from the claim. But the question is, like the die that I rolled 10 times and got all 6, is it far enough? Is it different enough? To be able to answer that, there are 3 different techniques that we can use. All right? I'm going to walk you through all 3 techniques. And we're going to start with the confidence interval. That's our good friend. Now, the confidence interval can be used because this is what is referred to as a two-tailed test. And the reason it's two-tailed is because this is a not equals. If this were, remember back here, if it were a less than, if it were a greater than, or it were a less than, it gets harder to use the confidence interval. And I'll explain why down the road when we start playing with those as well. All right? So the very first thing that we're going to do is we're going to build a confidence interval around this guy. All right, that's the first way to test it. So we're going to pick alpha equals 0.05, which implies that we're going to do a 95% confidence interval around. This is the nice little boilerplate way to start, around P. And we're going to see if 0.75 fits in that. Well, let's say if you remember your formula, the confidence interval around P was what? You take P hat, right? And you subtract the error term. And what was the error term again? It was Z sub alpha halves times, and then it was the square root. If, remember, we're assuming that this is our parameter. So I get to say 0.75 times 0.25. Remember, if we didn't, then we would assume that both P and Q are 0.5. And I divide that by N, which is 3,011. And that's going to be the left bound. On the right, it's going to be P hat plus Z alpha over 2 times the square root of, ooh, I'm going to run out of room over here, aren't I? Times the square root of, okay, dang it, everything's coming unwound. 0.75 times 0.25 divided by 3,011. All right, now we have to check a couple things first. Remember, when we deal with proportions, what we're really dealing with is kind of a binomial setting. And I know it's easy to screw those up, but one of the assumptions for being able to deal with this is to ensure that NP and NQ are both greater than or equal to 5. Well, that's easy to see. I mean, if I take 0.75 times 3011 and 0.25 times 3011, you're darn well sure we're going to be greater than or equal to 5. So we can cross that off. That's one of our assumptions when we're dealing with this. Now let's actually build out our confidence interval and see what happens. I take p hat, which is 0.73, right? Minus. Now, do you remember what the z alpha over 2 was for a 95% confidence interval? Well, that was easy, right? It was 1.96. Let's make sure. Let's back up just in case. If I stumble over here, I want to get to my z table and I want 0.025. Remember how this worked? I could go 0.025. Where's that guy? 0.25. 0.025 right there is negative 1.96 and positive 1.96. Because remember, sample proportions distribute themselves normally. Sampling distributions for proportions distribute themselves normally. So I got 0.73 minus 1.96 times the square root of 0.75 times 0.25, just building the confidence interval and checking to see if this guy is in there, divided by 3011, and 0.73 plus 1.96 times the square root of 0.75 times 0.25 divided by 3011. And that's going to be my interval. So using my fancy schmancy calculator, I really need to get one of those calculator programs where I can do this on the computer screen, but so you guys could catch all my ding-dong errors. So 0.73 minus 1.96 times the square root of 0.75 times 0.25 divided by 3011. In paren, I think I'm good there. I end up with 0.715 on the left, and if I hit second entry and change my minus to a plus, which saves me a boatload of time, I get 0.745. Uh-oh. Wait a sec. Notice this 95% confidence interval, which really tells us we're 95% confident that the mean should be in there. Now, here comes the lawyer math. Wait a sec, but we're only 5% confident that we could make an error. I could actually have chosen, just by random chance, that these 3,000 people were way too low. But we don't care about that, all right? We hope that everything went well and that our data values are valid, which they are as long as they were collected randomly. All right, now we're going to write this up. Since 0.75 is not, now this is fancy mathematics, since 0.75 is not in the confidence interval from 0.715 to 0.745. Now here's where we get into the lawyer speak, all right? There is evidence that the population proportion for internet users, for adult internet users, isn't 0.75. Now, why do we get to say that? Because what we actually did, since the null hypothesis isn't in this, we actually rejected the null. We rejected the null hypothesis. It doesn't live in this confidence interval. There's no way. If this confidence interval is correct, which we hope, I mean, we're 95% confident that it would contain the mean, well, then this guy better be in it. If it's going to be, you know what I'm saying? If 0.73 isn't different enough, then 0.75 needs to be in this confidence interval. And therefore, we're going to reject the null. Now, this method is using confidence intervals. And remember, it only works if we have a not equal to right there. If it's anything other, it's not going to work. All right, now, we're going to do an entirely different way of testing the hypothesis. Okay? So here it comes. Kind of buckle yourself in. There's going to be two more. But they're not... initially, when you start playing with these, they can be a little counterintuitive, but don't be afraid. So the first thing we're going to do is we're going to test the null hypothesis that it's 0.75. Now we know from the confidence interval that it already can't be that. All right? My alternative hypothesis, whoops, this is equal to P, and this is 0.75 is not equal to P. Now, what we're going to do here is find what are called critical values. And we've talked about critical values before. Values, and alpha equals 0.05. Now, what 0.05 is in this case, and I know this is going to sound redundant because we already found, quote-unquote, the critical values, but watch how this works. 0.05 is kind of the allowable probability of failure, but what it really says is we're not going to let this, remember, p hat equals 0.73 and n equals 3011. We are not going to let 0.73 drift far enough away from 0.75 that it ends up out here in crazy town. If after I take a value, a test statistic, and I'll show you the test statistic here in a sec, if my test statistic that I take ends up too far, if it ends up in this is called the critical region. Critical region, as is this, same thing, I'll call this the CR, okay, or the critical region, then that means that 0.73 was too far away from 0.75, and it's not going to work. Excuse me. The test statistic that we're going to use for this, let's get back to black, the test statistic, so the test stat, is it's just Z, and all that it is it's p hat minus p divided by the square root of PQ over N. Okay? Now, you may say, whoa, this looks kind of familiar. Well, it actually comes from the fact that, remember, my z-test for my binomial was, what was it? It was, think about it. It was, remember, we had NP, x minus mu, which was actually n times p hat, minus n times p, divided by root n PQ. If I divide everything by n, then I end up with p hat minus p. If I divide this by n, I end up with the root n in the denominator. So that's where it comes from. It's nothing fancy. And we don't have to worry about the whole central limit theorem thing because we think of this as that's all encompassed in this. Now, remember, if alpha equals 0.05 and we're on the standard normal curve, then that implies that this area over here is going to be 0.025 and this area over here is going to be 0.025 because of, whoops, that's supposed to be a 5, because of the symmetric property of the standard normal curve. Well, we already know what this critical value is. It's 1.96 and it's negative 1.96. Those are the z values that in this case, they're the line of demarcation between if I get some weird value in here, okay, that's allowed. I'm going to allow my value, my test, my point estimate to fall in here. But if it falls outside of there, something is fishy. I'm rolling the dice and I'm getting too many.